Hey, welcome back to DATQVAULT video lectures. Today we're going to start talking about some stereochemistry. This is lecture 2.1, which is specifically on stereoisomers. Stereoisomers are it's a very, very important topic in organic chemistry. It's actually probably one of the toughest topics to actually learn and comprehend. So I suggest that you pay a lot of attention to this lecture and um, try to work through it as best as you can. It's probably a lecture that you're going to want to listen to probably more than once because a lot of the topics are really difficult to grasp, and it's actually very important that you fully grasp these topics because they're not only going to be important on stereochemical specific questions on the DAT, but when you start to answer questions on like mechanisms and stuff, those questions often include a lot of stereochemistry themselves. So it's going to be really important to actually fully understand the whole stereochemistry topic and grasp it for later topics in organic chemistry. So this lecture might be a slightly longer than most of the other lectures. So if you want to break it kind of into two sections, I highly suggest it. Or if you can like stand to listen through the whole lecture too, that'd be great. But if you feel like you need to kind of rewind the tape a little bit and try to fully grasp some of the topics, I highly suggest it before moving on to some of the more complex topics in this lecture. So when looking at types of isomers, there's four main types, but we're only going to focus on three of them in this lecture. The first type of isomer is called a constitutional isomer, and constitutional isomers are molecules that have the same exact molecular formula or empirical formula, but the atoms are bonded to other different atoms within the molecule. And so the other kind of isomers are first enantiomers, and these molecules have the same connectivity, unlike constitutional isomers. But enantiomers are actually non-superimposable mirror images of each other. So all the atoms are connected similarly in two enantiomers, but when you take the mirror image of it, the molecules are non-superimposable. And you can look at this like as if you look at your hands, for instance. Your left hand and your right hand are both mirror images of each other, but you actually can't superimpose them on top of each other. So your hands are actually enantiomers of each other. So another kind of isomer is called a diastereomer, and these molecules again have the same exact connectivity, but these two molecules are actually not going to be mirror images of each other. Kind of a difficult concept to grasp, but hopefully by the end of this lecture you'll be able to distinguish enantiomers and diastereomers from each other. And the last kind of isomer is a geometric isomer. And these are labeled as cis and trans isomers or E and Z isomers. We kind of covered these in one of the nomenclature lectures on alkenes. So if you want to go back to understanding what geometric isomers are and how they look, I would suggest going back to nomenclature lecture 2. So the ones that we're going to focus on again are these three on the bottom, and these kind of isomers are specifically called stereoisomers, which means they have different orientations in space and not different connectivity. Alright, so one concept that we really need to understand when looking at when looking at stereoisomers is the concept of chirality. And this means an object has a mirror image that is different from the original object. And I gave you an example earlier, which are your left and right hands. They are mirror images of each other, but you cannot superimpose them on top of each other. They're completely different objects. So when looking at something that's more similar to a molecule, like this right here, we have a tetrahedral shape, which in the center we could envision that being a carbon surrounded by 4 different kinds of substituents. In this case, I just labeled the substituents A, X, Y, and T. They could be any kind of substituent, but notice that all the substituents in this example are completely different. So we're going to ask ourselves, is this object chiral? Does it have chirality? So what we're going to do is we're going to look at the mirror image of the object. And if we cannot superimpose that mirror image on the original object, then yes, that object is going to be chiral. So here we're going to take the mirror image of the object, and if you notice, this object over here to the right in the mirror indeed is non-superimposable over this image. So if you were to take and line up the A and the X again by rotating this object 180 degrees, you'll notice that the T would actually be back where the Y is, and the Y would be where the T is. And no matter how you flip or spin this object over here to the right, you cannot superimpose it on the image to the left. That means this image on the left is indeed a chiral object. And specifically when we're talking about organic molecules, we look for a chiral center. And that's the exact middle of the object where the chirality is based. If this were a carbon here, we would call that a chiral carbon. So let's take and look at an object that does not have chirality. In this instance, we just took the Y and replaced it with the T. So now we have two of the same substituents on this molecule right here, AX and just T. So now if we take the mirror image of this object, and again we just rotate it 180 degrees where the A and the X line up, you'll notice that this object is superimposable, and this object has no chirality. So this object is now going to be known as achiral. So it has no chirality to it. And that means this carbon center right here is not a chiral center. So that's a really, really important concept to learn when looking at chirality within molecules and determining if they're enantiomers and diastereomers and so forth. Alright, so let's actually look at a few molecules and try to identify the chiral centers. So this molecule, first molecule to the left right here, 2-butanol, we're going to try to identify the chiral centers within the molecule. So when trying to identify chiral centers, we look for a carbon center that has 4 completely unique different substituents coming off of it. You notice every other carbon in the molecule besides this carbon right here has at least 2 or 3 of the same substituents on it, which are hydrogens. So this has an ethyl group, a methyl group, a hydroxyl group, and a hydrogen. 4 different substituents, so this is going to be the only chiral center in this molecule. Alright, moving on to this molecule over here, we notice that this carbon right here has 2 methyl groups on it, so that is not a chiral center. This carbon over here on the far right hand side has 2 hydrogens coming off of it, so that is not a chiral center. The only chiral center in this molecule right here is actually the central carbon, which has a bromine, a hydrogen, and 2 completely other different substituents coming off of it. Alright, so looking at this molecule right here, down in the bottom left-hand corner, slightly trickier molecule. Again, we're looking at centers that have 3 completely different substituents coming off of them. If we look at this center right here, we'll notice that it has a hydrogen, an amine coming off of it, but if we go around the cyclic structure in either direction, we notice that they come to the exact same point. And if we travel left or right around the structure, it's the exact same. So these 2 substituents right here are the same substituent. And so this, in fact, is not a chiral center. And if we look at this center right here, we have a methyl group and we have a carboxylic acid. But again, if we travel around the ring in either direction, it looks the exact same. So this, again, is not a chiral center. So this molecule right here is overall going to be an achiral molecule. But if we put a methyl substituent coming off of it at this position, all of a sudden if we travel around the ring this direction, it looks different than traveling around the ring in this direction. So this center, and this center all become chiral centers in this molecule. Alright, now we're going to take a look at our last example over here on the right-hand side. So just remember that carbon chiral centers have to be sp3 hybridized, right? So that means it has to have 4 different things coming off of it. So this center right here is a chiral center, but this sp2 hybridized center right here is not a chiral center because it only has 3 different substituents on it. Alright, now that we know how to identify chiral centers, we need to know how to name these chiral centers. So let's take our good friend 2-butanol over here like we saw before, and we identified the chiral center in the molecule being right here. But chiral centers have 2 different geometries. And here are the 2 examples down here on the bottom. Either this hydroxyl group can be coming out at us, this being a tetrahedral center, or we can have the hydroxyl group facing back and away from us. These 2 objects right here, these 2 molecules, are non-superimposable. This means you can't take this molecule right here and lay it on top of this molecule and impose it on top of it. It's absolutely impossible. So these 2 molecules actually right here are enantiomers of each other. Because this molecule right here is actually the mirror image of this one. So how do we name these molecules differently? Because they're actually different molecules. We need to label the center as an R or an S configuration. And we do that by giving the substituents priorities, more or less. We always want to start by taking the lowest priority substituent and putting it in the farthest back position. So first, let's give this molecule the substituent on this molecule priorities. So the hydroxyl group is of course going to have the highest priority, the ethyl group second, and the methyl group third, and of course the hydrogen is going to have the lowest priority. So the lowest priority substituent in this molecule is faced back and away from us, which is good, that's what we want. And so to label this as an R or S configuration, we actually kind of draw a circle going from the highest priority to the lowest priority substituent and kind of form like either a clockwise or a counterclockwise rotation. This one going from 1 to 2 to 3 is going to give us a clockwise rotation, and clockwise rotation from highest priority to lowest priority substituent means we have an R configuration. So this center right here is going to have an R configuration. And when we write that out, this is going to be R 2-butanol. Alright, so this molecule over here just has the opposite configuration, so we can immediately give it the S configuration, but we're going to go through and learn how to give it the S configuration manually. So again, this is the number 1, 2, 3, and 4 substituents. Again, we have a clockwise rotation, but since the hydrogen, the lowest priority substituent, is faced out and away from us, we're just going to flip it from an R to an S configuration. So this would be S2-butanol. Another way you can look at it is you can actually just take this molecule and flip it over. So if we just flip this molecule over, we get the hydroxyl group facing toward us and the hydrogen facing away from us. So this is 1, 2, and 3 in priority. And now we notice that we're going in a counterclockwise fashion. So that's an S stereocenter. So either you can have the lowest priority substituent facing towards you and then just flip the configuration afterwards, or you can flip the molecule and then label your priority, and then you don't have to flip the configuration after figuring out if it's a counterclockwise or clockwise rotation around the stereocenter. Alright, so I suggest practicing this one a lot with a lot of different molecules in the practice questions to actually get good at this concept, because it's extremely, extremely important. Alright, so let's do a quick question here. This question asks us how many carbon stereocenters does this pretty complex molecule actually contain. So why don't you guys just take a second and try to identify all the chiral centers in this molecule, and then we'll go over and identify them together. Alright, so now that you've had a second to identify all the chiral centers within this molecule, we're going to identify them together. So the strategy that I would take, this molecule is actually a morphine molecule, a very, very popular pain-killing molecule. So I would start identifying the chiral centers by moving from the right-hand side of the or the left-hand side of the molecule to the right-hand side of the molecule, making sure we don't count chiral centers twice. So remember, a chiral center has 4 different substituents coming off of it, 4 unique substituents. We're only being shown carbons here. We're not being shown hydrogens, but hydrogens count as a substituent. So this right here is a chiral center. This is an all-carbon chiral center. This is another chiral center. This is a chiral center here, and then down here is also another chiral center. So this molecule actually has 5 different chiral centers in it. So I suggest maybe looking at a bunch of different molecules and then trying to identify chiral centers quickly and effectively, because questions like this will probably show up on the DAT. Alright, so we're kind of at the halfway point in the lecture here, so if you want to take a break and come back to it, this is where I'd suggest doing it. If you want to keep powering through it, let's go ahead and do it. So now we're going to try to identify what diastereomers are. Remember, the difference between a diastereomer and an enantiomer is a diastereomer, again, has atoms that have the same connectivity in the molecule, but the 2 molecules are not mirror images of each other. So if you look at these 2 molecules right here, we're going to try to figure out if they are enantiomers or diastereomers of each other. If you notice, the molecules have the same exact connectivity, but in this case, this fluorine is facing forward, this fluorine is facing backwards, and in this molecule, it's the exact opposite. So one way we can do this is try to figure out if this molecule up here is a mirror image of the molecule over here on the left. And so to do that, we can actually just draw the mirror image of the compound. So if we draw the mirror image of this molecule, we find that this molecule, if we just flip it over, is actually this exact same molecule down here. So because of that, these 2 molecules are going to be enantiomers. So how about these 2 molecules? Again, they have the same connectivity, but instead of switching both of the stereocenters, we're only switching one of the stereocenters. So we're taking this fluorine right here and having it face forward instead of having it face backwards. And so if we draw the mirror image of this compound, it's going to look like this. This molecule right here is still not superimposable with this molecule here over on the left, and because of that, these 2 molecules cannot be diastereomers of each other. Or sorry, they cannot be enantiomers of each other. They're actually diastereomers. Alright, so we're going to look at this molecule down here on the bottom right-hand corner. Again, we're only flipping one of the stereocenters around. So we're taking this fluorine right here and making it face backwards instead of forwards. Again, we can draw the mirror image of this compound. And the mirror image of this compound is, again, different than this compound. So these 2 compounds are diastereomers again. So a quick way to actually go about determining if something is a diastereomer or an enantiomer is if you flip around all of the chiral centers in the molecule, then you'll get the enantiomer. If you flip around just one of the chiral centers in the molecule, if the molecule has 2 chiral centers, then you're going to get the diastereomer of the compound. So for instance, if you look at these 2 compounds with respect to each other, you're flipping around both of the chiral centers in the molecule. So these 2 molecules are then enantiomers of each other. Alright, and then that means if you take the enantiomer and you take the mirror image of it, you're going to get the same compound. So these two compounds with respect to each other are the same. You just flip this molecule over and you'll get this compound. Alright, so let's go about doing this in a different fashion. You can either flip the molecule over and look at mirror images, which is what we just did, or you can actually label the stereocenters in the molecule and determine if the molecule is an enantiomer or a diastereomer. So we start by identifying the chiral centers, which are here and here, and then we can start labeling priorities in the molecule and give the stereocenter an R or an S configuration. So fluorine has the highest priority, followed by this substituent and then the ethyl substituent. So this is counterclockwise fashion because the hydrogen, the lowest priority substituent, is faced backwards. So this is an S stereocenter. In this stereocenter, the fluorine gets the 1 priority. Again, the 2 priority is this substituent, and then the 3rd priority is the methyl substituent. This is a counterclockwise rotation, but the fluorine is faced back and the hydrogen is faced forward, so this is actually an R configuration around that stereocenter. So if we look at this molecule, we flipped the configuration at this center, so this is now an R stereocenter, and the configuration around this stereocenter is flipped, so this is actually now an S stereocenter. So we notice we flipped the configuration of both stereocenters from SR to RS, so that means these two molecules are enantiomers because we flipped both stereocenters. So if we look at this molecule right here, we only flipped one of the stereocenters, so this is still an S stereocenter, and now the fluorine is faced forward, so it is now also an S stereocenter. So the fact that we went from SR to an SS now, we can determine that these two molecules are diastereomers. And similarly with this molecule, we went from SR now to RR. So these two molecules with respect to each other are diastereomers, but now these two molecules with respect to each other, we flip both stereocenters SS to RR, so these are enantiomers of each other. So there's two approaches that you can take to determining if things are diastereomeric or enantiomeric, and that's either by looking at the mirror images and trying to figure out if they're superimposable or not, or just by simply labeling the stereocenters and figuring out if you've flipped either one or all of the stereocenters in the molecule. Another important key feature with diastereomers is you have to have at least 2 stereocenters in the molecule for the molecule to be considered a diastereomer or not. Enantiomers can have, of course, more than one stereocenter, but diastereomers cannot have only one stereocenter in the molecule. So that's an important feature of molecules that are diastereomers. Alright, so let's quickly go to a question, and in this question we're trying to figure out if these two molecules are enantiomers, diastereomers, structural isomers, geometric isomers, or if they're identical molecules. So why don't you pause the video, take a minute, and try to figure out what these two molecules are with respect to each other. Alright, so I would say the quickest way to go about this question is to figure out what the orientation is around each of the stereocenters. So in this molecule right here, we're just gonna label the priority of the substituents. We're gonna start on the left-hand side and then do the right-hand side of the molecule, this stereocenter. In each molecule there are 2 stereocenters. So this substituent went right here, has the highest priority, followed by this ethyl group and then this methyl group. So we're going to travel in a clockwise position, clockwise rotation, which means the stereocenter is R, but notice the hydrogen is facing forward in this molecule. So we're actually going to give this stereocenter the S configuration. And then this stereocenter right here, this isopropyl group over here, has the highest priority, followed by this substituent over here, and then the methyl substituent. So the hydrogen is already faced back, and we're traveling in a counterclockwise rotation. So again, we're going to have an S stereocenter. So the first molecule has an SS orientation around both of these stereocenters. So let's look at this molecule over here, and let's start with the same stereocenter over here on this side. So again, the substituent here has the first priority, followed by the ethyl group and then the methyl group. So again, we're going to travel in a clockwise rotation, but again, the hydrogen is facing forward, the lowest priority substituent. So we're going to switch it from clockwise to counterclockwise, and counterclockwise is an S orientation. So now we're going to look at this chiral center here, just like we did over in this molecule. And number one substituent being the isopropyl group, followed by this substituent and then the methyl substituent. Here we're traveling again in the counterclockwise orientation. The lowest priority substituent already facing back, so again that's going to be S. We notice that these two are the exact same orientation. They are both SS, and because they're both SS, these two molecules are absolutely identical to one another. So you can easily see that they're actually identical to one another if you take this molecule and you just rotate it 180 degrees. You can actually completely overlap it with this molecule right here. So just remember, if you rotate the molecule, it doesn't affect the stereochemistry of the molecule. You actually have to change the stereochemistry around one of the carbons to change the stereochemistry of the overall molecule. Otherwise, the molecules are going to be absolutely identical. All right, so a quick recap on this lecture. I made up a nice flow chart for you guys to follow. You're not going to have access to this flow chart, of course, on the DAT. So it's a really good study tool, though, to help you differentiate between enantiomers, diastereomers, and constitutional isomers. So if you start with two molecules and the molecules don't have the same molecular formula, then of course they're not isomers at all of each other. But if they do have the same molecular formula, then you can determine if they're stereoisomers or constitutional isomers based on if they have the same name or not. If they have an R or S or a cis or a trans out in front of it, then they must be stereoisomers of each other. Remember, constitutional isomers also have same connectivity, so they're going to have completely different names from one another. If the molecules are mirror images of each other, then they're enantiomers. If the two molecules being compared are not mirror images, but they have the same connectivity, then they're diastereomers of one another. And then the two different diastereomers that you can have are geometric isomers and all other diastereomers. Geometric isomers being cis and trans, E and Z configurations, such as alkenes. But all the other molecules which have two or more chirality centers in the molecule would be considered diastereomers. All right, so I suggest, if you didn't completely comprehend everything in this lecture, going through it maybe once or twice more, and then try to answer a lot of questions on chirality. And like I said, this concept may seem kind of hard at first, but once you actually solidify this concept, it's going to be very important in understanding a lot of other concepts later on in organic chemistry and when understanding mechanisms of organic chemistry reactions.